So we're going to sketch the definition of the Donaldson invariants today. So remember last time we got ourselves in the following situation. So for a while we were pretending that we were going to do general G bundles, but then we didn't like reducibles, so we're going to take G to be really PUN, and we observed that first of all, if I look at the cohomology ring of PUN with Q coefficients, it's canonically really isomorphic to the cohomology ring of B SUN. That's not true over Z, but we only care about Q for the moment. And this is polynomial algebra in the Chern classes from C1, from C2 up to Cn. And then we saw that the cohomology ring of the G equivariant cohomology of the space of connections in such a bundle was isomorphic to a bunch of copies. Remember, we introduced this algebra A of X, which is the symmetric algebra on the two-dimensional homology of X and zero-dimensional homology of X. This was in degree 2, this was in degree 4, and then this was a tensor product of a bunch of copies of this with a shift. This one is sort of coming from C2. This one's coming from C3, et cetera. This is coming up from Cn. OK. So then if we fix our Riemannian metric G, X compact oriented four-manifold, that's a Riemannian metric. Then we have our moduli space, which is sitting inside, sitting inside space of connections. We'd rather that it was sitting inside irreducible connections, so we're going to choose P, this PUN bundle, so that it's sort of second Stiefel-Whitney class evaluates on some two-dimensional homology class to be K mod n, where K is a unit in Z mod nz. So this condition implies that for a generic metric, if B plus of X is positive, then there are no reducibles. OK. And it's important to note that this is preserved under bubbling. So if you bubble, you don't change this characteristic class. That's changing the bundle on a neighborhood of a point, which is not changing the evaluation of W2 on a two-dimensional homology class, right? And remember that this guy, for PUN bundle, that's an H2 of X with Z mod NZ coefficients, okay? So by some topological trick, we've managed to get rid of one problem. They're no reducible, so.
Sorry, the n, the little n and the big n are the same then? Z mod NZ.
Sorry, that's a big N. All n's are big. Yeah. Yeah. Okay. So, so this is preserved under bubbling, and slight lie, but we're going to assume that all moduli spaces are smooth. So for n equals 2, that's follows from generic metrics theorem of Uhlenbeck. For n bigger than 2, you need further perturbations, which I won't discuss. But so for SUN, or for PUN, yeah, actually that's also, just to make things a little more concrete. So we've got this PUN bundle, but let's suppose that this PUN bundle is the traceless endomorphism bundle of a honest vector bundle. Right. Then the characteristic class that we care about, P1 of add P, is in terms of the characteristic classes of E, it's 2n times C2 of E minus n minus 1 C1 squared of E. So, so the dimension formula, so the dimension of this moduli space, yeah, by the way, it's an exercise that you should do. If E prime is E tensor L, then this slightly complicated expression is unchanged. So if E is replaced by this guy, then that expression is unchanged. Right, which it had better be, because the endomorphism bundle is unchanged under tensoring by a line bundle. Right, so this characteristic class should have that same property. So the dimension of the moduli space, remember, is minus 2p1. So for n c2 of E minus 2n minus 1 c1 squared of E minus the dimension of SUN, n squared minus 1 over 2 times the other characteristic plus signature. So we're assuming that this guy's a manifold, yeah, of this dimension. Right? Now, and you notice that we had this notion of, I mean, this action of Z on these bundles by kind of adding or subtracting an instanton, that action just changes the second Chern class by 1. So, under bubbling, C2 of E changes by, well, if it's really bubbling, changes by -1 or -k more generally. All right, so the dimension, if some MP prime arises as an Uhlenbeck limit, the dimension of MP prime is equal to the dimension of original MP minus 4nk for some k. K in Z, k positive. Okay, so just to say that it's important to realize that as n gets bigger, the dimension drop gets bigger, right?
Why does adding an instanton drop the dimension of this?
So this is under bubbling, which is subtracting an instanton. I mean, sorry. So if I added an instanton, then it would be +1. Okay, but I'm thinking about what happens in limits, so I'm thinking about instantons evaporating, as it were. So the dimension, this guy, if it's a bubble limit, it should be in a moduli space that has smaller dimension. Right? All right, so now, the fantasy is that we take some class in here, some class of degree D, and I mean, again, I'm not going to explain why the moduli spaces are orientable and what it takes to orient them, but let's believe that. We want to take a class in here, and we'd like to evaluate alpha on some kind of fundamental class. This guy, when, what do we call this? Call that D. Right. So, but this, you can't do this. No, not compact. So we need to think a little bit more carefully about how we might be able to do such an, how can we recover something that looks like that? So it's important to realize, these are all polynomial algebras. So if we want to evaluate something in a polynomial algebra, it's enough to evaluate it on monomials in the generators. So maybe somehow that's a better thing to do. So let's think about a very concrete situation. So the problem. Sure. Yeah.
What do you need to perturb the entire moduli spaces for students?
Well, you need even in the four-dimensional case, you need some kind of version of holonomy perturbations. What? Some version of holonomy perturbations. So you're going to change. I mean, you need to construct some kind of nice maps that, so you need, the curvature gives you an equivariant, a gauge group equivariant map from here to here. And you have to construct out of your little bare hands other maps that are kind of mild to do that. And a way to start to do that is to, if you, here's my 4 manifold. If I pick a base point and look at the holonomy around this point, I can never mind. We won't define the Donaldson invariance if I start to just, but it takes more work. And oh yeah. Yeah. Well, I mean, lots of different places. I mean, it's in some of, a version of this is in some of Donaldson's very old papers. I mean, and then there's a paper of Peter's where he defines the Donaldson invariant, some version of Donaldson invariance, and generally explains this with some care. So maybe I don't remember, maybe 98, something like that. Okay, but what do I say? Yeah. Okay. So let's think about this once again a little bit more. So oh yeah, sorry. Yeah. Before we do that, I was going to. Yeah. So let's look at an example. Suppose we take, I don't know, X is a K3 surface. And G, well, let's make it SU2. So PSU2, so SO3. And let's look at a moduli space where some kind of bubbling could happen. So we're going to take I don't do this. So the dimension formula for K3 in this situation is, well, I'm going to do it that way. So it's 8 C2 of meat minus a quarter C1 squared of E. And then dimension of this guy's 3. And that's really 1 plus B plus. B plus of K3 is 3. So this is 1 plus 3. So that's, we got a minus 12 there. And we want to figure out what to do here. We want a situation where there's like there's one bubble happening. So what we're going to do is the dimension drops by 8. So it should drop. We want it to drop into something that's not empty. So we want to add 1 instanton to a 0-dimensional moduli space. 0-dimensional would have this thing be 12 to cancel 8 times this thing to be 12. And then we want it to be, we want this to work out to be, we want an 8-dimensional moduli space. So, how do I say it? Yeah. So in terms of P1, what did I want? Sorry. I wrote it down somewhere just so I would not do this, but anyway. What?
Maybe you were about to say this, or maybe you said this during the lecture where I was gone, but what exactly, when you're acting by an instanton, you're acting by the fork homology
Yeah, I mean, so the, you know, just as a kind of bookkeeping device, it's important to realize that there's an action of Z on bundles. And that action is to take a bundle on the force sphere of smallest Pontryagin class, say, and you just connect some with that, or take the sphere with the opposite orientation, same bundle, connect some with that, and that will change some characteristic class by plus or minus 1. And in this case, the characteristic class that it changes by 1 is exactly that funny guy. It's not P1. It's the minimal Pontryagin number isn't 1.
Oh, so you're literally just attaching something, like a model.
Yeah, you just connect something with some bundle over the force sphere.
So this is exactly the same.
Yeah, yeah, yeah. No, that's okay. So, anyway, yeah, I choose the bundle so this guy's, so the dimension turns out to be 8. So this thing should be 20. And you can figure out what these guys are. The interesting thing is that this guy has to have, so there's one thing to worry about, which is that, how do I say it? Remember, so that in terms of the Pontryagin number of an SO3 bundle is constrained to be W2 squared mod 4. And I'm going to take W2 to be Poincare dual to some class X, so that X squared is minus 2. So there's certainly such, K3 surface contains minus 2 spheres, so there's certainly such a class. And this is consistent with that. So such a guy exists. And now, what does the compactification look like? So I've got this 8-dimensional moduli space for X. Its Uhlenbeck compactification consists of, well, just the 8-dimensional moduli space, and then disjoint union of, or it's sitting inside, but turns out to be equal to 0-dimensional moduli space for the same. So there's some W2 here, which is fixed, and then times X. All right. So the picture, I've got this sort of very schematic picture here. I've got this 8-dimensional moduli space where W2 is fixed. And then in the boundary, it might have many components, but there's a 0-dimensional moduli space of X, and then there's a copy of X for each component of this guy in the boundary. Okay? Are we seeing that? Right? So they're just saying, this has some number of points. I don't know. In the picture, it has 1 point because it'll look uglier if I draw it with more points. But so that's what the compactification looks like. Now, what we'd like to do, let's take, say, 4 surfaces, so 2 chains on X, or maybe, let's imagine we took 4 2 chains, right? So think of them as smooth surfaces inside the 4 manifold. Then there's this mu map that we described last time coming from the second Chern class, which takes the second Chern class, well, the way I said it, sorry, the way I said it, but we should unpackage it. The game, the way I said it was that our model for this is sort of our model for the homotopy type of the space of connections that has an evaluation map to BSO3. And the way we got classes was by pulling back a characteristic class here to this product and then slanting with a homology class to get a cohomology class here. So there's evaluation star of C2 of the universal SO3 bundle over the fundamental class of sigma. Now here I have on purpose not taken homology class but actual cycles. I should do the same thing here. I should think of this as a particular representative for the second Chern class. So this is a particular cohomology, a particular cocycle on, well, not, I mean, as I've said, I don't see it as on the space of connections, and probably I should. I mean, I see it on something homotopy equivalent to the space of connections, but I should really see it on the space of connections. So let me describe how to do that. So there was a kind of nice homotopy model that allowed us to compute the cohomology ring rather quickly using standard tools, but we should have a little more geometric way of understanding the same construction. So what we're going to do instead, now we've arranged that there are no reducibles. So what I'm going to do is, so these are the irreducible connections in P, and I'm going to cross that with my principal bundle divided by the center of G. Okay, I can do that. That's still a principal bundle. Now the structure groups become the adjoint group, right? And on this space, the gauge transformations mod the center of the group acts freely. Right, because it acts freely here. So it acts freely on this product. So I take the quotient. And I'm going to call this U. And what do we notice? So this has a natural map to the space of connections mod this guy. That's what we were calling B star times X. Right. And what's the fiber of this? Zoltan. Are you not paying attention? Jeez. Bad students. Anybody else? What? G mod ZG. So the fiber is Z mod GZ, or the adjoint form of the group. So this is an honest principle. The fiber of this map. right? So, you know, how to say, right? I mean, the fiber, if I forgot about this, the fiber would be trivial, right? Because I'm just taking this thing, mod that, mapping it to this thing, mod that. Not much is happening. What happens over here? Well, if I take a point here, the thing that's sitting above there is the fiber of the principal bundle. In other words, a copy of this guy, fiber of this principal bundle. OK, great. So this is really a add G bundle, so PSUN bundle in our situation. And so it has characteristic classes now. And I can kind of do this a little bit in a slightly nicer way. So, you know, I need to fix some kind of representatives. And there's a bit of an art in that for C2 of u, C3 of u, et cetera, Cn of u as chains, cochains on the base. And now I can define a more concrete kind of mu map given given a cycle in ck of x. I can define mu I of alpha in that's going to be C I of alpha slanted, sorry, Ci of u slanted against alpha. Okay? So that's, you know, kind of need to think a bit that under the homotopy equivalence of this space with the mapping space, that this universal bundle is isomorphic to the pullback of under the evaluation map. So that's an exercise or whatever. I mean, in a sense, you should, you can take all of the algebraic topology that we've done as motivation. We don't need it. This is the one thing that we need, this construction. I mean, so we've got these mu maps, and then what we want to do well, I mean, eventually it might go beyond motivation, but I want to make a definition of how to evaluate certain, I'm going to take some monomials in this algebra, and I want to somehow from those monomials produce a number for you by doing something with a moduli space. Okay? Now, the fact that those monomials correspond to elements of the cohomology ring of the space in which the moduli space lives, that's great, but I mean, there's the obvious interesting question: do I have all of them? Right? I mean, have I gotten all the cohomology that there is? Maybe I've missed something, and the algebraic topology is telling you no. You haven't missed anything. You've written down, generators. So the observation from this point of view is that the induced map. So there's a map from the homology of X to the, sorry, how do I say it? Yeah. So, I mean, save time. So there are these n-1 maps to here, and the claim that we can now state is that the image generates the cohomology ring. Right, so that's the statement the algebraic topology allows us to make, but in a sense we don't necessarily care. Okay. And now what we want to do, okay, yeah. So now let's think about that in our example. So here we're going to replace this by C2 of U slanted against sigma I. All right. Now, when I do that slant product, how much of the bundle U does it use? You know, so over here, there's X, there's B star, all right, and I've got this universal bundle, and inside here I've got well, in fact, let's think of something simpler. Suppose I just took a point, an element of H naught. And I want to do the slant product. What does that give me? Peter, what?
It gives you the over B star.
Yeah. So all that's giving you the cohomology class that if I do the definition for a point, all it does is takes the universal bundle, restricts it to B star times a point, and takes the class there. So to say that a little more precisely, there's the cohomology class. So C2 of U slanted against the point in here, and B star, and H4 B star. This is equal to C2 of Ux in H4 of B star, where this is U restricted to B star times a point. Right? Now, think about what that tells you about bubbling. So let's suppose that that this point class was involved in a computation that we wanted to do. Right? So So to get a better picture of this, you should think of, because these are Chern classes, these have very, in the cohomology ring of you know, I mean, second Chern class of a C2 bundle, what's that? That's the Euler class, right, where a section vanishes. So thinking about it that way, I could think of that cohomology class as a codimension 4 gadget codimension 4 thing with a good enough normal bundle inside B star. And now, so I'll say, actually, I don't even need to say that to say what I want to say here. So you know, think about this picture again where we have this, this 8-dimensional moduli space. W2 is fixed on this K3, and its compactification. This is 8-dimensional moduli space times union 0-dimensional moduli space, same W. That's, I'll just call that X is still the K3 times X, right? Now, I've got this 4-dimensional cohomology class sitting here, and as long as I don't bubble to the point X, that cohomology class extends, right? Because you know, that cohomology class doesn't notice what's going on, doesn't know what's going on out here. In other words, if I, you know, to say it another way, I could think of that cohomology class as coming from the universal bundle on yeah. So I don't. Yeah. So there's this bundle. This picture is coming from some bundle P. This picture is coming from some bundle P prime. P restricted to X minus this point. Let's decorate it some more. Is isomorphic to P prime X minus that point. So if I do, you know, that's that's going to tell me that this cohomology class, you know, I can use the sort of same definition here and here to get a cohomology class as long as the you know. So the claim is that this cycle extends to a class on on this 8-dimensional moduli space union 0-dimensional moduli space times X, except for at the base point, I mean, except for the point that I'm using here. So okay, and now what, you know, so similarly, if I look at, you know, if I look at mu2 of a surface sigma, that gives me a class in H2 of the space of connections X for the bundle P. But this will extend to a class on in this, well, actually think about the moduli space on this M8 here. So it's a class in the two-dimensional cohomology. It extends to a class on, not on the full Uhlenbeck compactification, but on this thing, disjoint union, zero-dimensional moduli space X, but on X minus sigma, or maybe a neighborhood of sigma, if I wanted to be a little bit more careful. So we have these classes. They're not quite, well, they're not defined everywhere on the compactification. But now let's think about what happens when we start cupping them together. Right? When we start cupping them together, they might be defined on on more of the compactification. So the claim is that, say, if I take mu2 of sigma 1 cup mu2 of sigma 2, this is going to be defined on this 8-dimensional moduli space union 0-dimensional moduli space times X minus the intersection of these guys. Again, you might want to take neighborhoods. But you notice that once so these guys are two-dimensional homology classes. If they're in general position, then the intersection will be some points. And finally, if I take this guy is defined on on the whole compactification. And then finally, if I add the fourth one to get up to the dimension, that's still defined on the whole thing. And now it makes sense. Now I have this 8-dimensional manifold. I can compactify it by adding something. Yeah.
So a very basic question. So does the compactification work in the sense that, like, you sort of find an embedding of n, like you find like the x coordinates of n8, and then you embed it in b star cross b star cross x, and then it somehow just actually.
So I mean. Remember, the compactification is defined, by introducing the space of ideal instantons.
But do
right?
they somehow lie in that entire space?
No. It's not. They don't live in B star. So, but the the thing, how do I say it? Yeah. Yeah. And, so say, I'm not proving anything at all, right? But the point here is to, when you think about these classes more geometrically, you see that there's a kind of consistent way of defining them as a cohomology class on this space with the topology that we've given it. I mean, that's not trivial, but it's a thing that you have to do, as it were. And I mean, or, another way, so if you think about it more geometrically, if you represent this rather than as a cohomology class, well, I mean, there are different ways of telling the story carefully. One way is to think of, represent these Chern classes as actually Poincare dual to codimension 4 things, say, the second Chern class. So there'll be some codimension 4 thing that is representing this guy, and kind of the Poincare dual of the fact that it extends will say that it contains, the limits can contain things that are of the point m0 times that point. And, but then if I take, so for example, I mean, an important point, I should, if I wanted to evaluate, so maybe, if I want to do this.
You're saying that you could always do that?
No. Yeah. This is meaningless, what I wrote. The thing that means something is that I can take a represented, I can take C2 of the universal bundle restricted to a point x0, C2 of the universal bundle restricted to a different point. These are giving me each 4-dimensional cohomology classes on this guy, but these points are different. Okay, and then when I think about, that means that there's, each of them gives something of codimension 4 that that contains, the first one gives me something of codimension 4 that hits this part at the point x0. The other guy gives me something of codimension 4 in here that hits this thing at the point x1. Their intersection misses this. It only has intersection up here. So, the sort of, yeah. So an extremely schematic picture, which is too schematic to actually show what's going on entirely, but in something of a quarter the dimension. So a quarter of the dimension means this would be 2, and well, all right, quarter. Yeah, let's do quarter. Quarter is better. Yeah. So, sorry. Imagine. So the 2-dimensional bit, that's supposed to be like M8. This 1-dimensional bit is supposed to be like that. And then somehow my one representative hits the boundary at some prescribed point, and the other representative hits the boundary at some other prescribed point. Unfortunately, it has to hit in 2 because it's a 1 manifold, and that's a little different than what's happening in real life. But the intersection, is well defined provided I make sure I do that. But of course, just like in here, if I allow the points to come together, the intersection number might change. Right? So this is not what we're doing. We are doing this. Right? This thing evaluated on on M8 in some suitable sense. Now, and so that's sort of the game. Where was I? I think I'm here. So yeah. So I mean, it's so the definition, the Donaldson invariant for some principal bundle P, evaluated on some, we're just going to do n equals 2, but I have k surfaces and L points. I take cycle representatives. I need to make sure that these guys are represented by cycles that are transverse to each other, transverse to the points. The points should all be distinct. So the sigma I and xj are all transverse. And then I evaluate. Then it makes sense to do the cut product of all of these guys and evaluate it on an appropriate appropriate moduli space. But it's important to realize that it doesn't make sense kind of to nakedly evaluate just that. I could also take so this expression at the moment, I should think of it as a cycle representative of a cohomology class. And the answer really, honest to God, depends on the cycle representative. And in fact, it's not, I mean, that's it.
That expression doesn't, right? You take.
Yeah, that expression, I mean, this expression doesn't depend on the choice of representatives that satisfy these hypotheses. Okay, if they don't satisfy these hypotheses, I mean, and the claim is that in fact, as long as if you have two sets of representatives that satisfy these hypotheses, then the answer is the same. So it is, in some formal sense, defining a linear functional on the cohomology ring. But it's only because these are generators for the cohomology ring. But it's not like it doesn't sort of a priori make sense to just evaluate a given element of the cohomology on the moduli space. You have to define it through its definition on monomials. And then you can prove that for manifolds, and then you can find counterexamples to the H-cobordism theorem, et cetera, et cetera, et cetera. Anyway. That's it. Time's up. Sorry.
Do you want to say about how people actually make computations or how easy to make computations?
Well, it depends how good you are at doing computations. How are the theta functions? How are the theta functions?
Exactly.
See? Then it's okay. Any other questions?
So how do you compute it for K3?
Well, there are a lot of different ways to get at it. I mean, in fact, there's an elementary way to compute for K3, some invariant for K3, which is already interesting, which is, you know, if I think of the K3 surface, you know, nice model for it is I take T4 mod involution, and then I kind of, you know, I get, and I resolve the 16 singularities. Right. Now, what you can, so, yeah. So, remember, the dimension of the moduli space for K3 was, for an SO3 moduli space was this. If I want this to be 0, then I want P1 to be minus 6. And the interesting game that you can play, I'd have to think about this a little bit more to get this straight. But so, you know, so K3 is this. Let's take T4 minus these 16 4 balls, mod plus or minus 1, and then union 16 cotangent disk bundles. Right? I take neighbors of 16 fixed points. People can leave, but this is kind of a nice concrete picture of K3. Now, if you think about instantons for a little while, you can find that, you know, so, you know, so eventually, early on in the story, if you seriously want to study instantons, you can find small. You can see that there are some nice point moduli spaces on this guy, which you can understand kind of concretely from an analog of the ADHM construction. So you can really write down.
The analog of the what construction?
So there's this ADHM construction, a T. Edrinfeld Hitchin Manin, which tells you how to construct instantons on the 4 sphere and then eventually instantons on ALE spaces, of which this is an instance. So you can really, you know, there's some very concrete solutions that you can write down on this. This is point moduli space. And then you can ask, can I glue them to this guy? Well, this guy has rather big fundamental group. It has flat connections. And what you can do with a little care is you can show that you can get these zero-dimensional moduli spaces from taking, you need 3, kind of turn on 3 of these guys and leave the other 13 alone, and use a flat connection here. And you can, if you set it up carefully, there'll be a unique flat connection that can glue to these guys, and that'll give you a solution, which you really, I mean, you know, takes some cleverness. But that's in an old paper of Peter's, maybe That's quite a nice paper if you want to see how to do some things in it, just with very little technology other than knowing about solutions on here. You can actually prove, you can find solutions on log transforms of K3s and stuff like that. So you can really prove that there are, non-diffeomorphic form manifolds using gauge theory, but not a lot of tools, as it were. Any other questions? Maybe we can let Ali.
Karen over here,
We can let Ali go.